Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Map of highest peak, Leetcode 1765. In this problem, we are given an integer matrix isWater of size m into n that represents a map of land and water cells. 0 represents a land cell and 1 represents a water cell. For example, in this matrix, this is water cell and these are all land cells. And then we must assign each cell a height in a way that follows these rules. The height of each cell must be non-negative. So that means it should be 0 or some positive value. If the cell is a water cell, its height must be 0. For example, for the given water cell in the input, the height of the water cell in the output is 0. And any two adjacent cells must have an absolute difference of at most 1. A cell is adjacent to another cell if the former is north, east, south or west of the latter. That is, their sides are touching. So that means for this water cell, these two are adjacent cells, but this one is not. Because in this problem, when we say adjacent, we refer to only north, east, south and west directions and not the diagonals. And for each cell, we have to assign the height to the adjacent cells with the absolute height difference of at most 1. For example, for this water cell, for its adjacent cells, we can assign either 0 or 1. -1 is ruled out because we cannot assign negative values. And we assign 1 here instead of 0. Why? Because we have to find an assignment of heights such that the maximum height in the matrix is maximized. So that's why we will assign 1 here. And in the end, we return an integer matrix height of size m into n, where height ij is height of cell ij. If there are multiple solutions, then return any of them. Then in example 1, we are given this initial matrix where 1 is water cell and rest of the values 0 here denote the land cell. So we will initialize the heights matrix and assign height 0 to the water cells. And now for its adjacent cells, we can assign the height with the absolute difference of at most 1. So we will assign height 1 and 1 to these two adjacent cells. And now for the land cells which are adjacent to these land cells and are not yet visited, we can assign the height again with the at most difference of 1. So this height becomes 2 and this is what we are seeing in the output matrix. And this is how the values will be assigned. And in a way, if you notice, we are forming some kind of a BFS wave. But let's look at more examples. In example 2, for the given input matrix, these two are water cells. So in the output heights matrix, we will assign the value 0 for these cells. Now for this water cell, we will assign the land cells adjacent to it with the height difference of 1. So it will be 1, 1 and 1 here. Similarly for this water cell also we will do the same thing. So we will assign its non-visited adjacent cells with height equal to 1. Now these two land cells are remaining. So we will fill in the value from the adjacent cells. So it will get +1 from this point. So it will become 2 and this will also become 2. And this is the output matrix that we will return in the end. Now in terms of solution, as we realize during the example walkthrough that the problem needs a traversal where we start from the certain points, that is water cells, and explore their neighbors first. And for this kind of traversal, breadth first search fits in perfectly. And since we can start from multiple points, this kind of BFS is called multi-source BFS. So in BFS, we create a queue and add the coordinates of the water cells. For example, for this input matrix, water cells are at 0, 2 and 1, 0, so we can enqueue them. And also let's initialize the height matrix with initial height of -1 for the land cells and 0 for the water cells. Why -1 for land cells? I will explain it in a bit. And now we can start the BFS where we will dequeue a cell, explore its unvisited valid neighbors and update the height of these neighbors and add them to the queue and continue this process until the queue is empty. For this example, we will dequeue the cell 0, 2 and now we need to explore its neighbors. For that, we can use the directions array, which I have covered in similar problems in the past. For each cell, we can explore 4 directions: up, right, down and left, or north, east, south and west. And in the direction array, we can represent each direction as a pair of coordinate changes dx, dy, that is changes in x and y directions. which denote the unit change in coordinates from the current cell x, y in the specified direction. So we can use -1, 0 for going up, 0, 1 for going rightwards, 1, 0 for going downwards, and 0, -1 for going leftwards. So now for each cell, we can calculate the adjacent cell's position by just adding the cell's position with the directions coordinates. So based on this, we may get some cells that are out of bounds. So for example, for this water cell 0, 2, one of the neighbors we can get is by going up, which will result in row -1, which is out of bounds for this matrix. So we should ignore these neighbors. And now, how do we know if the cell is unvisited? And for that, we can actually use the answer matrix height. If the value of this neighbor is not -1, then the cell already has a height and is visited. But if it is -1, that means we are exploring it for the first time and we need to assign height to it. So for cell 2, 0, valid unvisited neighbors are cells 1, 2 and 0, 1. So we visit them by setting their heights in the height matrix. So we set their height by increasing the current cell's height by 1. Since the current cell is water and its height is 0 in the heights matrix, we will set its neighbor's height to 1 and then add them to the queue. Now we will dequeue next cell, that is 1, 0, and explore its unvisited valid neighbors, which are 0, 0, 1, 1 and 2, 0. So we will set their height equal to height of this water cell plus 1. So it will be 1, 1 and 1, and enqueue them to the queue. Now we will dequeue 1, 2, and for this cell, again we will explore the 4 directions, and only unvisited valid cell is 2, 2. So we will visit it and set the height of this cell as current cell's height plus 1, which is 1 plus 1 equal to 2, and enqueue this cell. Then we dequeue 0, 1, and for this cell all its neighbors are visited because we can see that in the heights matrix none of them have the value -1. So we will process next element in the queue, which is 0, 0, and all its valid neighbors are visited as well. So we dequeue next element 1, 1 from the queue. And for 1, 1, only neighbor which we have not visited is 2, 1. So we will visit it and set its height equal to 1 plus 1 equal to 2 and enqueue it in the queue. Then we dequeue 2, 0. It doesn't have any unvisited neighbors. Then we go to 2, 2. It also doesn't have any unvisited neighbors. And then we come to 2, 1 and it also doesn't have any unvisited neighbors. And now our queue is empty. So we end the BFS. And finally, our height matrix will be 1, 1, 0, 0, 1, 1, 1, 2, 2. And this will be our answer. So now let's jump into the code part. First, let's get number of rows and number of columns of the isWater matrix, let it be m and n, and create the answer matrix with same dimensions. Let's also initialize queue to facilitate the BFS process, and we will be storing the cell coordinates in it. Now we will iterate through each cell of the isWater matrix, and if the current cell is water, then we will set the height of this cell in the answer matrix to 0 and enqueue its coordinates to the queue. Otherwise, if the cell is land, then we will set height as -1 in the answer matrix, indicating it hasn't been visited yet. Now let's create a direction array representing 4 cardinal directions, that is north, east, south, west. Now we will start the BFS. So while queue is not empty, we will dequeue the cell and extract its row and column to I and j. And now we will loop through directions array, and for each direction in the directions array, we will calculate the coordinates of the neighbor cell ni and nj by adding the direction vector to the current cell coordinates. And if neighbor cell is within the bounds of the matrix, that is ni is greater than equal to 0, ni is less than m. Similarly, nj is greater than equal to 0 and nj is less than n. And height of this neighbor is -1, that is it is not visited yet. Then we will set the height of this neighbor cell equal to height of the current cell plus 1 and enqueue it to the queue. And once we are done with our BFS, we will return our answer matrix. So now let's submit this code. Cool. In terms of time complexity, it will be O of m into n, where m is number of rows and n is number of columns. Because we are iterating on the answer array twice, first to initialize it and then during the BFS. And in terms of space complexity also, it will be O of m into n, because we are using additional data structures like queue for running the BFS and storing the answer in the height matrix. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.